this so that Logan can look at it if he needs to. So circuits. So what we're looking at is how does current move around a full circuit? Keep in mind the analogy I gave you on the current is like the volume of the river and the voltage is like the strength of the current, okay? All right. All right, so DC current. We need to talk about some basic stuff. DC current is current that flows in only one direction, okay? Now, the problem is the current for most electrical devices is AC current. AC current's what kills you. DC is actually really better for you. AC current is on, off, on, off, on, off, on, off, so it pulses almost. And that's the problem. And it switches directions. That's what the on-off is, basically. If you're familiar with an oscilloscope, anybody know what an oscilloscope is? It measures a signal, okay? So, if you looked at an oscilloscope and you looked at current on an oscilloscope, and I'll get one up for you so you can see it, you would see DC would look like this, going across. This would be DC on an oscilloscope. AC on an oscilloscope, guys, would look like this, okay? And it's that up-down that's the problem. That's why I talk about the fact that if you're in computer class and you know computer's binary, AC is almost like binary. Forward, backwards, forward, backwards, forward, backwards, forward, backwards. Almost like on, off, on, off, on, off, on, off. That's kind of how you think about it, okay? All right, so we're only really talking in this one about DC current only, all right? AC current's a lot more complicated. Now, what's transient current? So we've got DC current, we've got transient current. It's temporary. Transient means temporary, doesn't it? Flows and then stops. When do we get a flow and a stop? The most likely time is when something's grounded. Think about it. If you put something to a ground, what happens? All the charge goes to earth and then it's done. That's what we talk about transient current. When you ground something, it's a transient current. And then we have continuous current. So if we look at continuous current here, it flows in a continuous loop to a power supply, provides an electromotive force, that's EMF. For those of you who don't know, electromotive force is EMF. That's what we have this script E for, okay? Supplies a constant electrical potential difference, okay? A battery is a continuous current, okay? Make sense? So now this is where I want to give you some additional facts. Let's talk about what a circuit is. We need to talk about circuit elements. We need to talk about circuit. First thing is, it is a way for voltage. Voltage is electric potential, right? To be transferred. From an EMF source, okay? To what we call a load. Now, what's a load? A load is like a light bulb. It's like one of your, an appliance. It's like a lamp, a heater, whatever. That's what you call your load. In other words, a load is something that uses electrical energy, okay? The source is connected to the load by what? In practical terms. Yep. By a wire. And the wire is your conductor. Okay? By a conductor. Why is it connected to the wire or conductor? Or conductor? Yes. It carries electrons, right? And the electrons are what carry electric potential with them. Guys, I need you to understand something. This is something that a lot of kids don't understand. A wire is not empty of electrons. Okay? When there's no source on it. It's not like it sits empty. There are electrons in copper, isn't there? Yeah. If there weren't, it wouldn't be a conductor, would it? So a lot of people think that when the light switch goes off, the electrons go home to the source, and they just sit there until you open the switch, opens a garage door, and they all come marching out. No. What's happening is the source is exciting the electrons, which begin to have what? Collisions, and they begin to get energy, and so then they begin to travel. They begin to travel around the circuit, right? But they're already there. It's not like they're all in a corral like a bunch of sheep and you open it and they all go, no. It's like they're everywhere. They're in a line, but now they're excited and now they all begin to move. Make sense?
Yes.
It's like taking still water. If you have a pond, a river that's got a gate, but there's still water, you've still got water sitting. When you open the gate, though, you get additional flow, don't you?
Yeah.
Okay. That's what the source is. It's the energy. It's like whipping up everything to make it want to move. Okay? So, things you need to know about current. It flows, what? Yep, downhill, so to speak, right? From high potential to low potential. And high potential is positive charge, right? And low potential is negative charge, okay? Current is due in a solid conductor. It's due to the flow of free electrons. Notice I say free electrons. Now it's going to flow, since it's electrons that are flowing. The free ones are jumping, aren't they? Jumping, and they're moving around. The free ones are moving. That means all the ones that aren't free are still there, though, aren't they? They are moving from negative to what? Positive, right? Okay. They're going to flow towards positive charge. Towards a positive charge. However, the electrons flow toward positive charge, but we say the current flows from what? Positive to negative. So here is a good, decent diagram that I think will help explain it. We've got positive end here, negative end here for our battery, right? So now we have it going to a light bulb. Correct? Hey, it even looks like a light bulb. Go me. So, what I want to do is I want to specify that current flows this way, right? But electrons flow that way. Because remember, electrons flow from negative to positive, but we consider the current to flow from positive to negative. And guys, this positive to negative flow is what we call, this flow from positive, this is called conventional current. It is our current convention, right? Thank you, Benjamin Franklin. So conventional charge flows from positive charge to negative charge in a conductor. Okay? But electrons really actually flow from negative to positive. All right. So charge, the other thing I want you to know is this. We know charge flows from what? From a source to a load, right? All right. And what we call a circuit. Okay? It arrives at the load with high energy and leaves it with lower energy. Okay? Why?
So the energy was used.
Yeah. Mm-hmm. Exactly. It leaves it with lower energy. So if we look at a typical circuit, we've got a source, right? It's got a positive end and a negative end. The source is going to go to some sort of a load. That has a positive to a negative, right? Charge with high potential, right? Goes this way, goes across our load. Potential is used up. So now we have charge with low potential. It then goes through the source again and gets what? Yeah, gets more energy. Battery is a chemical, usually it's a battery. A lot of times the battery is a chemical reaction happening. It will continue to happen and continue to send out that voltage until the chemical's all used up. That's what makes the battery used up. If it's a wall switch, it never gets used up, does it? It just keeps feeding more juice. So now, last thing I want to talk about here before we get. After leaving, the current circulates to the load, right? Then the load consumes potential, electric potential. But not current. The volume of the river doesn't reduce unless you branch it off, does it? You still have the same amount of water, but the strength of the flow might reduce. Get it? Because we put a load there that's an impediment. It sucked up some of the energy. Think of it almost like a sponge. It sucked up some of the energy out, and so it's still flowing, but it's not flowing as hard, as strong. Okay? How we feeling about this? Feeling okay so far? Kind of understanding it? Good. So now let's talk about resistors in series. This will make sense from the standpoint of volume versus strength. If we have two resistors in a circuit, okay? Two resistors in a circuit in series. They both have the same what? They're in the same current flow. So I is the same for both. I does not reduce, right? But in series, the potential is dropped. Why? I want you to look at the derivation here. If we have a voltage, the voltage is voltage 1 plus voltage 2, okay? But the I is the same. Voltage 1 is IR sub 1. Voltage in 2 is IR sub 2. So if you look at the voltage total equaling voltage of 1 plus voltage of 2, voltage total is IR equivalent, right? Well, that's equal to I times R1 plus R sub 2. So if you get rid of the I, what do you have left? Added up. So when they're in series, we add resistances in series. That's the big thing. Okay? EQ is equivalent resistance. However, now we got to look at resistance in parallel. Resistance in parallel is different, guys, because what's happening in parallel? Look at this circuit in parallel. We're branching, aren't we? We got a branch that goes this way and a branch that goes that way. So now what's happening is what's splitting? It's not the voltage this time, is it? It's the current. Just like branches of a river. The volume is changing, isn't it? So does it make sense that I is going to split up, but V is not? The strength is the same. It's just going to split into two smaller streams, isn't it? Two strong smaller streams, but two streams. So the V stays the same, but the I changes, okay? So look at what we have. This time, instead of saying V equals V1 plus V2, now we have I equaling I1 plus I2, okay? So what is V? So we know V equals IR, right? So what we know is I must equal V over R. Okay? That's where we're coming from. That's where this comes from. So I sub 1, since we know the voltage doesn't change, voltage the same and the current splits. Since the voltage is the same, every time we find I sub 1 is going to be V over R sub 1, isn't it? I sub 2 is going to be V over R sub 2. And I is going to become V over R equivalent, right? So if we divide everything through by V, what do we get? Yeah, 1 over R equivalent equals 1 over R plus R sub 1 plus 1 over R sub 2. So now I want you to think about this. What happens if we have resistors in series? The resistance increases, doesn't it? Do you agree? If we're just adding the resistances, the resistance goes up in series, right? So in series, R goes up. However, look at this guy. When resistors are in parallel, overall resistance goes what? Down. The current's going to split proportionally down the branches. And the current is going to take, more current is going to take the path with less resistance. Makes sense, doesn't it? If you have less of an impediment, more of the water is going to flow in that direction, right? More of the current's going to flow that way. All right. If one branch has no resistance whatsoever, all the current will go down that branch. And you know what we call that? We call that a short. You remember what happened when we had the source connected and it bypassed the resistor? What happened to the source? It caught up fire. Isn't that what happens with a short? Don't we have a problem with a short? It'll pop your circuit breaker, won't it? And the circuit breaker's there to keep a fire from happening. It'll overheat your source, basically.
Is that what a fuse is?
Mm-hmm.
Okay.
A fuse is a big old resistor, basically, that breaks. It's meant to melt if it gets too much current going through it. That's why you have them in your, that's why they pop in your circuit. And in the old-fashioned ones were screw-in, and they literally had a fuse that they had a little resistor in there that would burn up. And so it would, yeah, it'll burn. And then you'd have to unscrew it and put a new one in. These days, what they have is the switch is flipped. The switch is flipped automatically. When the current load gets too big, high on it, and it starts to overheat it, it automatically causes it to flip a switch that opens. And so it stops the circuit. You get an opening in the circuit, a switch open in the circuit, which is why, if you notice what happens when you have one flip like that, you reset it. You have to push it this way, and then you have to click it to reopen the circuit or to reclose the circuit. That's what's happening with those circuit breakers. That's why they're called a circuit breaker. Get it now? It puts a break in the circuit so current can no longer flow through that branch. All right? Because we don't want things to heat up and catch fire. Power is shared both in both and parallel. Okay, so what happens? In parallel, they have the same potential, but the rate at which the potential is carried, the current is decreased. So what do we know in this one? Voltage the same and current splits. So they're exactly the opposite. If they're in series, current's the same and voltage splits, or adds, right? But if they're in parallel, voltage the same, but current splits. Make sense?
Yes.
All right. So, let's talk about the rest of the basics. And you're going to see this relationship, by the way, in your lab that you're doing, which is why I'm having you do the lab before I have you do any kind of homework at all. All right? Meters. We talked about this yesterday, but let's talk about why meters. Why do we put an ammeter in series, but we put a voltmeter in parallel? Think about why that is.
Like, think that measures the...
An ammeter measures current, and a voltmeter measures voltage, okay? Ammeters, think about why we put it in series. Current is constant in series, isn't it? But it's not constant if it's in parallel. So if we want to measure the current, we have to put it in series. We have to put it in one branch, not across two branches. Because across two branches, how are we going to measure it? You see what I'm saying? Understand that if you tried to put an ammeter, the leads of an ammeter, like here and here, it's not really going to work, is it? you're not going to get a right reading, because what happens here? You've got current going here, but then part of it's going to split here and part of it's going to split there, isn't it? So we have to put it in series. We either have to put the ammeter here, or we have to put the ammeter here, or we have to put the ammeter here. We can't put it across something. We can't put it in parallel. Across is parallel. In series is in line. Does that make sense? Okay. Because you got to understand how current works. You want to measure the flow, you got to measure it in one spot, not try to measure it in two spots. And in parallel is two different spots. Does that make sense?
It's because it's different
Yeah.
across the circuit, but it's
Yeah.
not different across
It's not different in series. Yeah.
circuits.
You're just one branch. You're measuring the flow in one branch. So it's in series. However, voltage does change. So we have to measure it across the load, don't we? We know it's reducing, so if we want to know what the voltage is, we have to do it in parallel. In other words, in parallel means it's across the load. Okay? So voltage is constant in parallel, isn't it? So the voltmeter is placed in parallel. Current is constant in series, so the ammeters are placed in series. Voltage is constant in parallel, so voltmeters are placed in parallel. Ammeters are low resistance. Voltmeters are high resistance. Think about why that is. They're low resistance, so they don't affect the current. Ammeters, you're measuring the current, so you don't want to affect the current, so it's low resistance. But voltmeters, you don't want to affect the what? Current, do you? In other words, you don't want them to draw current. You're trying to measure the voltage, so you don't want them to draw current. It's a funny way to say it, but it's basically that's the case. All right, so that's what this picture shows. You need to know how to do stuff. When we draw a circuit, an ammeter is always drawn as a circle with an A. A voltmeter is always drawn with a circle with a V. And we always draw it in parallel. We draw an ammeter in series. Remember, this is the symbol for a battery, right, or a source. Longer piece is the positive, the shorter piece is the negative. And resistors are the little squiggles, okay? Got it? If we have resistors in parallel, we draw them in parallel. All right? Now, if we have batteries or sources in parallel, we draw them like, that's two batteries, okay? So we would do plus, minus, and we just add them, okay? All right. Everybody pretty happy with this so far? Circuit networks. Let's talk about circuit. Yeah, okay. So we're going to go off script again. I want to talk about circuit networks and how we draw circuits. Yeah, maybe. We might get to them, we might not. I'm taking my time with this as much as I can because this is one of the things that you really can use. In practical purposes, this is something you can use. All right? Drawing circuits. When we draw stuff, we need to show all of the elements, okay? We usually draw stuff in square diagrams, even if it's in reality it's not square. Don't draw, we use rectangles, etc. So if we do combinations, you've seen one, resistors in combination, series, parallel. We can have just series. We can have just parallel. So let me think about this. So just in series. We have a source, right? Plus, minus. we would draw one resistor, a second resistor, back to the circuit. Just because they're not laying next to each other doesn't mean they're not in series, okay? Everybody understands that's in series? We could draw them next to each other too. Now, just in parallel. This one's a little trickier because we got to draw one resistor, and then we draw, so this would be R sub 1, and this would be R sub 2. Okay? That's just in parallel. Now what happens if we have a combo plate? We have them in series and in parallel. We got a source here. This is my voltage source. Now, this is a combination. There are infinite number of combinations, guys. Infinite number of combinations. Okay? I want you to think about that. So this is our voltage here. We know which way is our current going to flow?
Current. So positive and negatives just gonna go around.
So this is I, right? Now what's it going to do at that junction? What's the current going to do at the junction? It's going to split, isn't it? So it's going to split, and you'd have I sub 1 and I sub, well, we'll call this 1. We'll have I sub 2 and I sub 3, won't we? And it's going to go through and across, and then back to here, and then what's it going to do? It's going to go back to being what? I sub 1 again, isn't it? Now, how much I sub 2 and I sub 3 are depends on what the resistance of 3 is and resistance of 4 is. It's going to go to the path of least resistance, isn't it? Have you ever wondered about that phrase? The path of least resistance? Well, yeah, we usually think of it as the easiest way, but it kind of comes from circuit stuff. The path of least resistance is going to get the most current, isn't it? So if R sub 3 is less resistance than R sub 4, the majority of the current is going to go through R sub 3, and less of it's going to go through R sub 4, isn't it? So now, let's talk about the voltage. What happens to the voltage in this circuit? We start with, let's say there was 9 volts here. We're going to have 9 volts going into resistor 1, aren't we? Are we going to have 9 volts coming out? No. So we have less voltage here. So let's say how much voltage we have depends on what the current is and what the resistor is, right? But we know the voltage is going to reduce here. Then the voltage is going to what? Reduce again here, isn't it? Because it's going across another resistor. However, the voltage doesn't reduce here, does it? So it stays the same, and then the voltage is going to reduce going across this guy, and it's going to reduce going across this guy, isn't it? Yeah? And then it's still reduced. It doesn't get bigger again, because remember, every load reduces the voltage, doesn't it?
Okay.
It does not reduce the current flow around the circuit. Current flow stays the same all the way around. It may split, but it'll come back together again, doesn't it? So the current here is the same as the current here. The water flow, we don't lose water. However, voltage says we lose strength, doesn't it? Does that make sense? We don't lose volume, but we do lose strength. So it's going to go down, it's going to go down in strength. It's going to stay the same strength as it splits, but then it's going to go down and go down here, which means what comes out is still reduced to here until it gets re-energized and then goes again. Totally makes sense? Yay. Good. I'm glad. So now we are at 9:40, I think it is 9:40. So we got 9:46. We get time to do a couple of things where we actually start looking at doing some sort of, while we have time here. Did I finish that? Calculations here, okay? It says determine the current in the 2 ohm resistor and the potential difference across the 2 marked points A and B when the switch is open and when the switch is closed. Notice that's a switch symbol. Switch symbol is like a doorway, right? It's like a gate.
Okay.
Open gate, no current. Closed gate, current. Okay? So how do we do this? So let's start with the switch open at A. We want to know the current at the 2 ohm resistor. If the gate is open, I want you to think about it. What do we know? This is positive, this is negative. So we know our current is flowing this way, isn't it?
Right.
It's going to continue to flow this way. Now, if the gate is open, is it going to flow and branch off?
Nope.
Nope. So we got the entire current still flowing this way to this guy, don't we? All right. So how do we figure out what the current is? We've got what? Voltage and a resistance, don't we? Yes? But we don't have just the resistance there. We got to figure out what the equivalent resistance is, don't we? So this is where it's fun, equivalent resistance. In other words, we got to look at all of the resistance in the entire circuit.
And the next part is a split circuit, or
Mm-hmm. Yep, it's tough, isn't it? So now what? So we got to look at this circuit and figure out what's in series and what's in parallel. These two right here are in parallel, aren't they?
Yep.
So we got to figure out what that resistance is. And then we go and say this and this combination are now in series, aren't they?
Right.
Make sense? So we got to figure out what our resistance is. So let's do that. So to figure out this resistance right here, let's do this first. We'll call this R sub 1. This is R sub 2. This is R sub 3. However you want to do it. So to find the resistance, we have to do, they're in parallel, so it's 1 over 4 plus what? 1 over 4? Is what? 1 over R, right?
Right.
So 1/4 plus 1/4 is what? 2/4, which is 1/2. So 2/4 is 1 over R. So now R is 4 over 2, which is what? 2 ohms, right? So this is the equivalent. This is the equivalent of 2 ohms, guys. Do you see that?
Okay.
Do you see how I got that? I did the parallel calculation. 1 over 4 plus 1 over 4 is 1 over R. Now, why did I do that? Because now this and this are in series, aren't they? So now I have to take that 2, I have to take R plus R over 3 and get what? We get 4 ohms. So we get 2 plus 2 is 4 ohms is equal to R equivalent. Now I can do what? V equals IR equivalent. Okay? So now let's plug in. What's V?
That's what we're looking for, right?
Yep. No, we're looking for I. We know V. 12-volt battery source.
It says turn. Oh, just turn right there.
Remember, the current's the same all the way through, right? So now that we know what's going on with the resistors, we can figure out what the current is. The equivalent resistance, I times what, 4? So what is I? 3 amps, right? Now that's A. Now we got to look at B. What happens if this switch is now closed? So now I'm going to get rid of this because we're going to start all over again. All right. So our switch is now closed. So now we have current going this way, right? And it's going to go this way. Now you're going to be tempted to say it's going to split, aren't you? But what did we say about current? Well, now it'll split if there's any resistance at all, won't it? But here's the problem. Is there any resistance in that branch? If there's no resistance, what was the caveat? If there's no resistance, all the current will flow through the path with no resistance, won't it? So what happens is it's pretty much bypassed this guy right here, and all of the current is going to go this way, isn't it? Does everybody understand why that is?
Yes.
If there had been a resistor right there, it would have split between the two resistors, proportional to how much resistance there was in each one. Okay? Now, it's now going to go there. So really what we have is the equivalent of 2 resistors in parallel, don't we? Remember, V is equal to IR equivalent. And didn't we figure out what our equivalent was here?
So,
It was 2 ohms, wasn't it? Dadgummit. So V, which is 12 volts, is equal to I times 2. So what is the current now?
6 amps.
6 amps. Is a 6 amp current because there was less resistance to the flow. Okay? Does that make sense?
Yes.
All right. I want to stop here. We're at a good place to stop. We'll talk about example B and this solve the circuit shown. We've got to figure out, let's at least figure out what the maybe figure out what the resistance is. But we're going to have to talk about Ohm's law and how that plays in. We're going to have to talk about Kirchhoff's loop rule at some point. And that's what I want to kind of look at the next time through. But before we talk about Kirchhoff's loop rule and before we do any more addition subtraction stuff with these and actual doing circuits, I want you to do the circuit lab. So you don't have, your only homework this time is to do the circuits lab, all right?